All right, so we can, there are a lot of ways, how do I want to say this? There are a lot of ways we can gain information about the solutions to differential equations without solving them. So in chapter 1 we talked about slope fields. I mentioned when I was talking about the test. Slope fields, critical points, equilibrium solutions. So we can gain some information about the solutions in that way. I wrote sometimes we can't solve differential equations, and then I amended that. Often we can't solve differential equations analytically. So it doesn't take much of a change to any of the equations that we looked at in chapter 2, the first order differential equations. It doesn't take much of a change to one of the equations, an extra x or an extra y somewhere, for us not to be able to solve them using analytic techniques. In those cases, we approximate the solutions with numerical methods. The easiest method uses the tangent line to approximate solutions near specific points. It is kind of similar, and I know you talked about Euler's method in BC. You also talked about Newton's method for finding zeros of polynomials. It's kind of a similar idea. So I'm just going to illustrate the idea. It's not complicated. It's not difficult to do, and thankfully computers are really good at doing it. So Euler's method. We want to, our goal is to approximate the solution to, we have an initial value problem. Y prime equals f of xy, and we're given y of x0 equals y0. So we're relying on the fact that this function gives us, y prime is the slope. A function gives us the slope of the tangent line at a specific point. So the equation of the tangent line to the unknown, we don't know the solution, y of x, is y equals y0 plus the slope at that point times x minus x0. So this is the slope at x0, y0. And I'm going to move this over a little bit and say at the point x0, y0. So that f of x0, y0 gives us the slope at that point. And this is our lovely point slope form of our equation of a line. And just a reminder, we've talked about this a number of times in various contexts. We call this the linearization of y of x. At that point. And we sometimes write and I think we did this for equation of a vector equation of a line, something like that. L of x is y0 plus f of x0, y0 x minus x0. So when you see this L of x, that's just talking about the equation of that tangent line at that point. I'm going to switch pages, and then I want to draw a little picture so we can kind of visualize what's going on here. And hopefully, by now, this idea of approximation using a tangent line, in Calc 3 we approximated using a tangent plane. That's a pretty standard technique for a lot of things in calculus. So here are my axes. And here's some curve. That's my solution curve. And here's that point x0, y0, where we're constructing a tangent line. I'll do my line in blue. So this is my tangent line L of x. And I'm going to extend my x-axis a little bit. I need it to go a little further out here. Oops, I'm in the wrong color. There. There we go. So what we're going to do, we're starting here, we construct our tangent line, we have that equation, and this is at a point, this is our x0. Now we're going to move a small distance, h, along the x-axis. To the point x1 equals x0 plus h. So I'm going to move some distance over here to x1 equals x0 plus h. And we're going to call this point x1, y1. So the approximate value of our function at x1 is L of x1 is y0 plus the slope times x0 plus h minus x0. This is my new x value. This is where we started. Well, x0 plus h minus x0 is just h. So that's just y0 plus h times f of x0, y0. And we get that y1 is approximately y of x1. And again, x1 is x0 plus h. So we're approximating our function value here by this y1. And if I go up here a little higher on my curve, this would be the actual value. This is the point x1, y at x1. That would be the actual value on our solution curve, the y value on our solution curve at this point x1. And this little bit here is our error in the approximation. So we get an approximate value based on the tangent line. And how good an approximation it is depends on the function, and it also depends on our choice of h. If we pick h very small, we tend to get a better approximation. If h is large, worse approximation. If the function grows extremely rapidly, then maybe suddenly the slope of the function changes, then maybe our approximation isn't as good. Now we can repeat this process. Using the point x1, y1. y1 is this our approximation. And we're going to use that as the starting point. And it's approximately on the solution curve. And we do this, we construct a tangent line using the slope of our function at this point. And then we move a slight distance, h, along the x-axis, and we get a new y value approximation at a point on the curve. So x2 equals x1 plus h, which I could say is x0 plus 2h. And y2 equals y of x0 plus 2h equals y of x1 plus h, which is approximately y2 equals y1 plus h times f of x1, y1. Because the change I'm making in the x is just h each time. And this gives us our slope at that particular point. And we continue doing this process. We get a new approximate point on our curve. We use the slope at that new point to construct a new tangent line to get us a new approximation for a point on our solution curve. A little further when we go h distance along the x-axis again. And we continue. We get that y of n plus 1 equals y of n plus h times f of x sub n, y sub n. And x sub n equals x0 plus nh, where n equals 0, 1, 2, dot, dot. So we iterate this process. We use our new point to plug into this to get another new point. And in that way we continue until we get to the x value at which we're trying to approximate the y value. So we're given x0, y0, that's our initial condition. And we have some other point, some distance away from x0, y0 that we want to approximate the y value. So the points that we get from calculating our tangent line are approximating the solution curve as we continue this iteration. So not a difficult process. And again, computers are really good at doing this. So let's take a look at an example. We won't have to do a lot of these by hand, but we do. It's good to practice a little bit to understand the process. So y prime equals x plus y squared, and y of 0 equals 0 is our initial condition. And we want to approximate y of 0.2. And we're going to start with h equals 0.1. Then we will do h equals 0.05. So we know y sub n plus 1 is y sub n plus h times x sub n plus y sub n squared. This is what gives us our slope at any particular point. This is our function. And for this, for the first approximation, we're using h is always going to be 0.1. That's how far we're moving along the x-axis with each step of this approximation. So y1 equals 0. That's y0, this point that we're given, plus 0.1 times x0 is 0 plus, that's x0, this is y0 squared, equals 0. So x1, y1, our first approximation is 0.1 comma 0. y2 is 0, which is y1, plus 0.1 times x1, which is 0.1, plus y1 squared equals 0.005. We'll do 0.005. So x2, y2 is 0.1, comma, 0.2, because I've gone 0.1 from there, 0.2, 0.01. Whoops, this should be, I was reading down from my next approximation. That's 0.01. So this is our approximation of y of 0.2 with h equals 0.1. So we needed 2 iterations to go from 0 to 0.2 using h equals 0.1. So our approximate value of our function is 0.01. For h equals 0.05, we're going to have to use a few more steps to get from 0 to 0.2. So y1 in this case is 0 plus 0.05 times 0 plus 0 squared, which is 0. So x1, y1 this time is 0.05, comma 0. So this is y0, this is x0, and y0. y2 is 0, which is y1, plus 0.05 times 0.05 plus 0 squared, This is x1 and this is y1. And that one gives me 0.005. So x2, y2 is 0.1, because we've gone 0.05 from here. 0.0025. Y3 is 0.0025 plus 0.05 times 0.1. This is Y2. Sorry, this is, yeah, that's Y2. This is X2 plus 0.0025 squared. That's Y2. And that gives me 0.0075. So X3, Y3 is 0.15, 0.0075. And our next iteration is going to get us to x equals 0.02. Sorry, 0.2. Y4 is 0.0075. That's Y3 plus 0.05 times 0.15. That's X3 plus 0.0075 squared. That's Y3, and I get 0.0150. So our final value, x4, y4, is 0.2, 0.0150. And that's our approximation using h equals 0.05. So I get another decimal point in our approximation. So not difficult to do by hand. Tedious to do by hand, yes. Computers are very good at doing this. So for the most part, we will use a computer. I have a couple of calculators in our Schoology folder. I'll do this before it logs me off. I have one Desmos calculator. So Desmos Euler's method calculator. Oh, I did a contour plotter. I don't want the contour plotter. Euler's method calculator. So here's our differential equation, f of xy. That's y prime equals f of xy. So x plus y squared. I'll put that in there. X plus y squared. X0, I'm going to set down to 0. Oops. Y0, I'll set to 0. And h it says n is the step size. We're going to do 0.1. And let's see, do I need to zoom? There we go. So it shows the iterations here. The x values, 0.1, 0.2, 0.3, and the y values. So we just need the second x value, 0.01 is what we came up with as well. So with this one, you have to, it does more steps than we necessarily would. So we could use it to approximate different points. So you have to look at your x values, say, oh, it's the second one that we got there, so I need the second y value. If we change the step size to 0.05, zoom in a little bit. So there are x values, 0.05, 0.01, da, 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 da. So here, for the fifth value, sorry, the fourth value, we get x equals 0.2 is what we were looking for. And they give us a few more decimal points than we calculated. 0.05, 0031. So that's a nice, the Desmos calculator is nice. In your homework, and in the book, it talks about how the Euler's method is generally not actually used as an approximation and application. It's not super fast. It's not super accurate for the amount of calculations you have to do. There are other approximation methods that are used. One is called Runge-Kutta. It's two different people's names. One mathematician, German mathematician, was Runge, R-U-N-G-E, and the other one was Kutta, K-U-T-T-A. So I have another calculator. One of your homework problems asks you to do Euler's method and Runge-Kutta method. You don't have to know how to do the method to use the online calculator. And it asks you to compare the solutions. So in our folder there, Wolfram Alpha Numerical Solver. And it says Runge-Kutta, but we can change that. If you change that to Euler's method, it will do it automatically. So you can do either or both, Euler's method, and what do we have? X plus y squared. Y0 equals 0. From 0 to 0.2, h equals 0.1. Oops, not 0.1. 0.1 equals. And there's a nice graph, and there are our steps. And if we wanted to do compare it to the other method, and there's the solution curve for the Runge-Kutta method. There's the Runge-Kutta method. I'm not sure. I would have to look. I don't remember off the top of my head exactly how Runge-Kutta works. But Runge-Kutta generally a little more accurate, a little quicker, and you can see the difference. See the difference in the solution curve that it produced.
It looks a little better.
Yeah, so it got here in one step. So, the very last problem, number 11, asks you to solve using Euler's method on the computer and Runge-Kutta, and just it asks you to do some comparisons. I think there's only one. Is there one or do one by hand in the homework?
What, Euler's method?
If what by Euler's method?
Euler's, what is it?
Euler.
Is it Euler's?
It's Euler, yes.
Euler's is the same thing.
Pretty much. Pretty much what it looks like.
Yeah, do you ever wonder, his name is pronounced Euler, but do you ever wonder how Euler would have pronounced Euclid?
Yes, that's what I'm saying.
Maybe. All right, questions? Okay. This is 2.6. Oh, I forgot one thing. No, I need to tell you something for one problem. 11. I just can't.
I think a 9 would make sense.
I think I erased that. No, yeah, there's a 9. 9, and then
Well, look, 1, 3, 7, 9. In the range 7 to 11.
I just thought it was too much repetition. The thing that I need to add is that if you can solve the differential equation analytically, so you can solve by hand or you can use a solver that will solve it exactly, you can compare the approximations with the actual solutions. So there's one problem, one of the homework problems asks you to compare actual solutions with your approximations. The absolute error, just so we have some terminology here, is the absolute value of the actual value minus the approximation. That's just the difference. The relative error is the absolute error divided by the absolute value of the actual value. The actual value of the quantity you want to calculate. And the percent relative error is the relative error times 100.
Would it be the same for absolute error if you want to find the percent?
So the absolute error is just going to be the difference in your approximated value to your actual calculated value. Yeah, so this will be some kind of decimal. This turns that decimal into percent. So there's one problem that asks you to make a little table and calculate these things. Yeah, so number 11, do with the Wolfram calculator, so you can compare the Euler's method with the Runge-Kutta method. And on the test, I will ask you to do one Euler's method problem by hand. But you'll just have to do a couple of iterations, just to show you know how to do it.
it's a 50-50 shot where we add like 6 choices or there's
Right. Do you get all the zeros in there?